Probably we won't finish Chapter 5. I'll probably do some of Chapter 5. Okay, we're on. Are there any questions? Is that a question or just a quizzical look?
Well, I might have a question.
Okay.
Last class when we talked about queues in tandem,
Yes.
we were left with the question of the traffic pattern that leaves the first group of servers
Yes.
and arrives at the second group
Yes.
of servers. And I'm still curious to know if this is a Poisson process or if it just looks like a Poisson process.
Okay, that's the key question. So where we were last time was this. We were looking at this model. We have Poisson arrivals with rate lambda. We have S1 servers in stage 1 with exponential service times with rate mu1, and we have block customers delayed. In other words, a queue is allowed to form. And then the output of the first stage is the input to the second stage. And the second stage, we have S2 servers and exponential service times with rate mu2. And of course, we could have a third stage and so on, but we only wrote the equation for 2. And what we found is that the joint probability at an instant in equilibrium for the number of customers in stage 1 and stage 2 factored into the product of the marginal probabilities for each individual stage. So what we did is we wrote the rate out equals rate in equations for these things, and then we found that if we substituted into those equations these probabilities, where this is the probability that describes stage 1 by itself in isolation, which is obviously an Erlang delay model, and this has the same form, except that its parameters are the same lambda and S2 and mu2, then we found that this is what happened. So that means that the number of customers in each stage are independent of each other. And furthermore, it means that the second stage has a state distribution just as if the output from the first stage was a Poisson process. So that raises the question, is it? And either possible answer is surprising. Because suppose I said that the output is a Poisson process. Then what that means is that the departure process, let's draw a picture of it like this. These are the departures. If the output is a Poisson process, we know that it has rate lambda because everybody who arrives leaves. And in fact, the distribution that we saw over here is the distribution we would have if, in fact, this stage wasn't there and these guys went directly there. So if the output is a Poisson process, that means that the departures from stage 1 must be, the times between departures must be independent, identical, exponential, and they must all have parameter lambda. In other words, the average time between these departures must be 1 over lambda. Now that seems very unlikely because remember that when all these servers are busy, we already know that the departure process has exponential into departure times, independent of each other, but that the rate is S1 mu1. In fact, we already used that argument when we derived the waiting time distribution. So we know that when all the servers are busy, the times between departures are exponential, but not with rate lambda, but rather with rate S1 mu1. We also know that during the times that all servers are not busy, the departure process is something else, because the rate at which the customers leave the servers depends on how many busy servers there are. The smaller the number of busy servers, the more time there is between departures. So it doesn't seem, it would be very surprising if somehow or other that all came out in the wash and that when you got done, the departure process was independent of S1 and mu1 and has only to do with lambda and in fact has independent and identical inter-departure times. That seems to be, that would be amazing. On the other hand, what is the other possibility? The other possibility is that this process is not a Poisson process, but that it nevertheless produces the same distribution here as it would if it were a Poisson process. Of course, that's possible because simply saying what a distribution is doesn't say what caused that distribution. So a state distribution is not uniquely determined by an arrival process ordinarily. So therefore, either way would be surprising. Okay, the answer, which I can't prove yet, but we can prove later, is called Burke's theorem. Or that's what it's called nowadays. Sometimes, yeah, Burke's theorem, sometimes called the output theorem. And what it says is that the output process from an MMSQ, that is Poisson input, exponential service times, S servers, and blocked customers delayed, which is what we have here, in equilibrium, we have to have equilibrium, is a Poisson process. See, interestingly, suppose we didn't have equilibrium. That is, suppose the lambda were greater than the S1 mu1. Suppose that this Q built to infinity. Then these servers would always be busy, and the output process would again be a Poisson process, but its rate would be S1 mu1 and not lambda. Because that's actually the easy case to see. The hard case, what's surprising is that when lambda is less than S mu, no matter how much less, as soon as it's less than S mu, then the output is still a Poisson process, but now its rate is lambda. So this is sometimes called Burke's theorem. This is a very famous theorem. It was proved in, first published in 1956. MMS? Equilibrium means that the offered load here is less than the number of servers, so we don't have an infinite queue. If we had an infinite queue, then the result is obvious, except that then the departure, then the input rate to queue number 2, stage number 2, would be S1 mu1 rather than lambda. Okay, so this is an amazing theorem, and it's the basis for a whole industry concerned with applications of queuing networks to modeling things like manufacturing processes and data communications. Now, this theorem was proved basically because of this result. That is, this result was found originally by Jackson. And in fact, there were two Jacksons. I'll get into this in a moment. There was J.R. Jackson and R.R.P. Jackson, and they were both working around the same time, which is in the early 50s. And I'm not sure which one. I think it was R.R.P. Jackson was the first one who got this result. And so this suggested the fact that the output process might be a Poisson process. Because if it isn't, as I say, then you have the strange thing in which the state distribution that you see in the second stage is just as if the output process were a Poisson process. So that would be very strange. So that suggested to Burke that this might be true, and Burke proved this theorem. And it was published in the journal Operations Research in 1956. And immediately there came other proofs, which we can again get to later on in the course. But one of the strange things about this was that this theorem is so counterintuitive in a sense that some people, knowledgeable people, thought that it must be wrong. And Burke's proof was not mathematically rigorous. You could say that. Of course, it could be made mathematically rigorous, and it was correct. But strangely, based on his proof, was some other facts that themselves he took as being obvious, but which weren't proved, but turned out to be true. And we'll get into that later. That's an interesting look, I think, into the what lies behind the way papers are published in science. So we'll get to that get to that soon. I'm very familiar with all of this because my office, when I worked at Bell Labs, was right next to Burke's. And he was sort of my mentor. If you notice in the front of the book, he's thanked for helping out and reading the manuscript. And in addition, there are some things in the book that are due to him which were never actually published. So I had the advantage of having access to memos that were written at Bell Labs by him which were not officially published, and so therefore could not be quoted as such. but nevertheless, I had the results, so I was able to get them into print for the first time, as far as the outside world, the world outside Bell Labs was concerned. So, in any event, at the moment, we don't have the tools to prove this, but it's true. And this leads into the next question, because now the thing to do is to take a look at exercise number 8, called networks of queues. So let me draw the picture here, and then let's apply all of this stuff to that case. So this is exercise number 8 on starts on page 135. And you have the complete solution in the solutions manual. So the idea is this. We have now a bunch of nodes or stations, whatever you want to call it, and we have arrivals occurring at rate lambda. So this is a Poisson process, and we'll have, let's say, S1 servers here, exponential service times with rate mu1. And then from there, we'll go, let's call this Q1. And then from there, we branch out. So let's call this Q2, this Q3. Now the idea here is that this is an MMS queue. In other words, it's just like the first stage here. But now when I leave this stage of service, then I, in a sense, flip a coin. I make a Bernoulli choice. And with probability P12, I send the customer to this stage. And with probability P13, I send them to that stage. And then, let's say, for the sake of this example, that there's another stage, which we'll call Q4, and everybody from Q3 goes to Q4. But coming out of Q2, let's say there were 2 branches, again chosen the same kind of way. That is, with probability P24, you send the guy to Q4, and with probability P2, you send them outside the system. And then the people, when they come out of Q4, go someplace else. So that's the system we want to analyze. So this system was first analyzed by J.R. Jackson, I think, if I remember this correctly. Okay, but J.R. Jackson was the first guy who put feedback in. That's the important point. So let's look at it without feedback. So now what we can do is we can write the state equations for this. Okay, so let's write them. Now we have P of J1, J2, J3, and J4. And we're going to equate, and of course each J corresponds to its individual stage. And now what we'll do is we'll equate the rate out of that stage to the rate out of this state to the rate into the state. So how can I get out of the state? Well, I can have an arrival from stream 1 or to stage 1. All that does is increment that guy by 1. And then what happens? Okay, now I can have a departure from stage 1. So a departure from stage 1 is either going to go to here or to here, but either way it's going to cause a change in state. So that's going to be, let's call that mu1 of J1. So this is the same notation we used before when we wrote the equations for this, where this mu1 of J1 is S1 mu1 when J1 is greater than S1, that is when there's a Q here, and it's equal to J1 mu1 when J1 is less than S1, depending on how many servers are busy there. Okay, so this term here then corresponds to a departure from stage 1. Okay, now what else can happen? Well, I could have a departure from stage 2, and what that'll do is it'll somehow change the state because this guy will decrease by 1, and either he goes away or this one goes up by 1. And similarly, okay, so let me write that. That would be mu2 of J2. And then I could have the same thing from here. So I have plus mu3 J3, and then I could have the same thing from here. Mu4, should I give myself more room? Okay, so let's see. So we have plus mu3 J3 plus mu4 J4, and all of that is multiplied by P of J1, J2, J3, J4 equals. Okay, so this is the rate at which I leave this state, and now I have to equate that to the rate at which I enter that state. So let me see if I can figure out how to do this. I could be in state J1 minus 1, J2, J3, J4, and have an arrival from outside. Okay, now what could happen? Okay, now let's suppose that I have a departure from here. So there are two cases. If I have a departure from here, I could be in state J1 plus 1, J2 minus 1, J3, J4. And then a departure from here that goes to here would cause that to drop by 1 and that to increment by 1. Okay, so what's the rate at that occurs? At which that occurs? Well, it would be mu1 of J1 plus 1. That gives me the departure rate from here, but then only a fraction, P12 of them, go in that direction. And likewise, there's going to be a fraction, P13, that's going to go in that direction. So that means I'm going to have a term like this. Mu1, J1 plus 1, P13, P of J1 plus 1, J2, J3 minus 1, J4. Okay, now what else can happen? Well, let's see. I could be in the state in which there is one more guy here and one less guy here and have that transition. So let me put that term in. I could be in state J1, J2 plus 1, J3, no, we got to make it, yeah, J3, J4 minus 1, and have a departure from here go to there. What's the rate at which that occurs? Well, that would be mu2 of J2 plus 1 times P24. Okay? So I've taken care of transitions from here to here. Now, similarly, I could have somebody from here who just leaves. Let me put that here. So I could be in state J1, J2 plus 1, J3, J4, and have a departure from stage 2, which occurs with rate mu2, J2 plus 1, and then leaves. So that would be P2. Okay, now what about this guy here? Well, let's see. I could be in state J1, J2, J3 plus 1, J4 minus 1, and have a departure from here who necessarily goes to there. And that rate would be mu3 of J3 plus 1. And finally, I could have a departure from here, and he necessarily leaves the system. So that would be the probability of being in state J1, J2, J3, J4 plus 1, and have a departure from stage 4, which would be mu4, J4 plus 1. Okay, so what I did now was I wrote down the equations, which I hope are the same as the ones in the answer book on page 87. And looks good so far. Okay, just let me check before I make a fool of myself. So we got mu2, J2 plus 1, J1 minus 1, J2 plus 1. Okay, so does this look okay to everybody? Let's see. Looking for a specific term here that I want to make sure I got. P2. Now something looks different here. First of all, oh, wait a minute, here we are, P2, J1. Yeah. Okay, everything looks okay. Does anybody have the answer book? Okay, there's a solutions manual, which everybody should have, of course. And on page 87, this problem's worked out. So if I haven't made a mistake, I've written down the equations that are on page 87. Okay, but if I hadn't made a mistake, that's okay, because you're supposed to spot it. This is just to see if you're alert. Okay, so these are the probabilities, are the state equations. Now, what's the answer? Well, the answer is, if you accept Burke's theorem as being true, then we can write down the answers immediately, because look at what's happening here. We could say that we have Poisson input coming into here, so therefore by Burke's theorem we have Poisson input leaving. So we have Poisson input leaving. Now if we make the decision as to how to direct the departures, we make that without regard to the state of the system, so we don't introduce any memory. Then, as we know, a Poisson stream that's decomposed with no memory decomposes into two independent Poisson streams. So that means that that's Poisson input and that's Poisson input. That means that this by itself is an MMSQ and this by itself is an MMSQ. So that means that the output from here, that's a Poisson stream, and the output from here is a Poisson stream. Now, if we take that output, which is Poisson, and we again decompose it into two streams, if we do it by a coin toss without introducing any memory, then this stream is Poisson and this stream is Poisson, and they're independent. And since these two streams are independent, then these two streams must be independent. When I take two Poisson streams and combine them, if they're independent, then the result is again a Poisson stream. That means that this is Poisson input to this stage, and therefore this is just an MMSQ. So that means that I can analyze this model term by term. So I know immediately what the answer is by Burke's theorem. That is, what I know is that the probability that I'm looking for, J1, J2, J3, J4, must be equal to the product P1, J1, P2, J2, P3, J3, P4, J4. And now what are each of those P's? Well, this is, the P1 is for the Erlang delay model with input lambda, and in fact I can redraw it. Okay, so now I'm going to redraw it so that for Q1 it looks just like that. So the P1, J1 describes that. Okay, now what about Q2? The P2, J2 describes Q2, and the way I would get the answer would be I would replace this link by a Poisson stream whose rate is the original rate, lambda, multiplied by the fraction of it that goes there, so it would be P12 lambda. Okay, what about stage 3? Well, the same argument is for stage 2. Now the lambda that goes here is P13 lambda. And what about Q4? Well, now the lambda that goes there is the lambda that comes out of here, which is P13 lambda, plus the lambda that comes out of here, which is P12 lambda, except that that has to be modified by P24. That is the original lambda. P12 is the fraction of it that goes this way, and P24 is the fraction of that goes this way. So here is the P24, and all of that is multiplied by the original lambda. Okay, so what I did was I took each of these stages and I replaced it by an independent stage as if the rest of the system didn't exist, just properly adjusting the lambdas. So now I go to my Erlang delay model, the state probabilities, and I plug in for those probabilities right there, except that I replace the lambdas by the equivalent lambdas, and I use the parameters as being, in this case, S2 mu2, S3 mu3, and S4 mu4. So I get the answers, I plug it back into the equations, it's going to work because if Burke's theorem is true, it must work, and so I'm done. So now I see that, for example, if I wanted to calculate how long it took to flow through this system, then all I have to do, say on average, is calculate the average number of customers here, and the average here, and the average here, and the average here, for which I have formulas, and add them up, because the average in the whole system is the sum of the averages. So then I have the average number in the system. I have the rate at which they enter the system. I have the average number present. So by Little's theorem, L equals lambda W, I must have the average time a customer spends in traversing the system. So I can get a lot of information that way. So this kind of stuff is what makes complicated networks solvable, because you break them down piece by piece. Okay, so Burke's theorem is great, and it's justified, or you can justify this method of solution. You can check it by simply assuming it's true, substituting it back into here. Now that's a lot of algebra, because you got to get everything to cancel out, and you got to show the left-hand side is equal to the right-hand side. But that's all done in the solutions manual, and it's just algebra. Okay, so that was part A. Now it says part B. It says consider the same network as in part A, except that now the portion of the output from Q2 that does not go to Q4 feeds back as input to Q1 instead of leaving the system. Write and solve the equations that determine the equilibrium distribution of the number of customers present at each Q. And it says that networks of this type with feedback were first considered by J.R. Jackson, 1957. Okay, so here's what happened. 1956 or 5 or so, I believe it was the other Jackson, wrote the equations for Q's in tandem and saw that there was a product solution. And so then Burke proved that the reason for that was because the output from each stage was a Poisson process. And so then J.R. Jackson, the other Jackson, comes along and he says, okay, let's consider this model. And he says, well, we already know what this is from Burke's theorem, so let's put a little bit of a spin on it. Let's take this guy here and feed back. And now what happens? Okay, now the equations are more complicated. But if you think through them, let's go term by term. I think if you think through them, the only term that's going to change is going to be the term that corresponds to departures from stage 2. So in this case, with probability P2, what happens is the customers leave. And so the only change is that this is reduced by 1. Now what happens if they feed back? If they feed back, that term isn't going to be in there, but instead there'll be another term which I'll write right below it. Mu2 J2 plus 1 P2 is still the departure rate from stage 2. Now, in order to get to this state, the J2 must be J2 plus 1. The J3 and J4 are not going to be affected by this transition. But now, instead of the transition, the departing customer going away, he comes back here and he increments the number here by 1. So that means that the number that fits right in there can't be J1 anymore. It must be J1 minus 1. So this term is replaced by the one below it. Okay, let me go through it again. If I had no feedback, then a departure from stage 2 leaves the system. So that reduces by 1. Nothing else has changed. So if I reduce this by 1, I get to this state. But now with feedback, if I'm in a state like this, where I have J2 plus 1 here, when he feeds back, he goes to there. So that means that what must happen in order to get to this state means that this one must be 1 above that, and this one must be 1 below that. Because what happens instantaneously with the feedback is that decreases by 1, and that increases by 1, and that will get me to this state. So the equations are the same except for these terms. But those terms are structurally very different. I mean, it makes all the difference in the world. So what's the solution? Okay, the solution as stated by Jackson is, well, it's got to be the same solution, except that we have to change the lambdas. Okay, now why is that? Here's Jackson's argument. He says, well, let's see. We have Poisson input here, so by Burke's theorem, we have Poisson output. So by the same argument as before, that's Poisson and that's Poisson. So that's Poisson. Now what about this? Well, that's Poisson and that's Poisson. Okay, now I take that, I feed that back to here, and I say, well, that's Poisson and that's Poisson. So adding them together makes everything Poisson. And so the end result is that nothing changes, except I have to change this parameter here, because I have to recognize that the lambda that comes in here when I do this decomposition, mental decomposition, is bigger. It's not the original lambda, it's the original lambda plus the amount that feeds back. Okay, so he says, okay, the answer is the same as before, except that now we have a new lambda, which I'll call lambda star, where lambda star is the feedback lambda. And now, throughout here, all the lambdas are now the lambda stars. Okay, so that's going to be lambda star, lambda star, lambda star. So all I have to do is figure out what lambda star is. Okay, now he says, well, every electrical engineer studying servo mechanisms knows how to do this. Or you could imagine, for example, that this is a continuous system and there's just water flowing through here. So you imagine a certain amount of water is forced through this pipe, and a certain fraction of that comes back, and then a certain fraction of that comes back again, and so forth. So what do you get? Okay, so let's see. So what I want to do is I want to write out what lambda star must be. So the total new input, lambda star, must be the original amount that goes in lambda, plus, now there's a certain amount that's going to go this way and go back. So what's that going to be? That's going to be P12 P lambda. So that's the amount that goes like this and then comes back through here and is fed into it again. But a certain amount of that is going to come back. How much of that's going to come back? Well, that's going to be P12 P squared lambda. But a certain amount of that is going to come back. How much is that going to be? It's going to be P12 P cubed lambda, and so on. So we have the original amount plus the fraction of that that returns, plus the fraction of that that returns, plus the fraction of that that returns, and so on. So you get this infinite series. Okay, now to solve the infinite series, what I do is I factor out the lambda, and then I see that I have 1 plus something squared plus something cubed, and so on. So that's a geometric series. So if I know that 1 plus x squared plus x cubed plus and so forth is equal to 1 over 1 minus x, as long as x is less than 1, then for this case, this is all equal to 1 over 1 minus P12 P. Because, of course, P12 times P is less than 1 because it's probabilities. So, in other words, the lambda star that fits here is just the original lambda modified by this factor. Of course, this factor is greater than 1 because P12 P is a number that's less than 1. So this is a multiplying factor, expansionary factor. And so it says that the new lambda is the old lambda times this factor, which makes it bigger. And the biggerness is the effect of the feedback. So what J.R. Jackson does is he says, okay, here's the solution, but now what we're going to put in these equations, which now have this term instead of this term, we're going to put in there is we're going to put in exactly the same product as we had before, except that in place of lambda, we now have lambda star, which is the original lambda times that. Now, does that work? And the answer is yes, because if that's what J.R. Jackson found, and if you go to the solutions manual, it just shows you put it in there and everything cancels out, and again you have a solution, which is truly amazing because you have changed the form of the equations substantially by putting a j minus 1 instead of a j1 there. But nevertheless, the solution is exactly the same except for a constant factor that floats around multiplying each lambda. So you would think it would be amazing, but J.R. Jackson says, no, that's not amazing, because that's what Burke's theorem predicts. I mean, it may be amazing that it works, but we shouldn't be surprised because the way we got the answer was we didn't just solve the equations. We assumed that the solution was given by that because Burke's theorem predicts it has to be that. And people thought about that a while. Actually, Burke thought about it for 15 years. And in 1972, he published a paper, and he says, well, actually, he says, Jackson's wrong. He has the right answer, but he has it for the wrong reason, because, in fact, Burke's theorem doesn't apply. Okay? Because Burke's theorem was derived under the assumption that there was no feedback. Now, what happens if there's feedback? If there's feedback, then what that means is that, at least it's conceivable, that this stream and this stream are not independent. So if I'm adding two streams which relate to each other, because remember, these guys are just the same as these guys except displaced in time, then I'm combining two streams which are not independent, and so therefore the argument that I'm combining two independent Poisson streams and I get a Poisson stream is not true, or it may not be true. The fact is it's not true, because in Burke's paper in 1972 he proved that it's not true. So what that means is that brings us back to the original question of Burke's theorem, because the original argument was, well, what's going on here? We solve these the equations for this model, and we say that if we have a lambda here, then what we find here is exactly what we would get if the first stage didn't exist, but we had Poisson input to it directly with rate lambda. And one possibility is that that's because the output process is a Poisson process. And the other possibility is that it's not a Poisson process, but it produces the same states as a Poisson process would. And the answer is, but it turns out to be a Poisson process. In this case, the exact opposite is true. In this case, what Burke showed, and which everybody now knows, is that in any network with feedback, the internal flows are not Poisson processes. But nevertheless, the states that they produce are just as if they were Poisson processes. So the argument as to the necessity of Burke's theorem is clear, because that's true, but it's not true because of Burke's theorem. Burke's theorem does not hold in here because of the feedback. In fact, here's a quote from the book. It says that the networks of this type with feedback were first considered by J.R. Jackson in 1957, who observed that, as in Part A, the results are the same as one would obtain if the input to each Q were a Poisson process. Jackson remarked that this was, quote, far from surprising in view of recent papers by P.J. Burke and E. Reich. And I might add that E. Reich wrote a paper in which he also proved Burke's theorem after Burke did, but he proved it by a different argument called reversibility, which turned out to be very important. But Burke was the one who saw the truth of it first, and then Reich came up with a somewhat more elegant argument. Okay, now, okay, so that's a quote, far from surprising in view of recent papers by P.J. Burke and E. Reich, unquote. However, as Burke in 1972, 15 years later, points out, Jackson's results are in fact quite astonishing, because the combined input to any Q that receives feedback is not Poisson. And here's a quote from Burke's 1972 paper. The point is that in networks without feedback, not only are the states of the component Qs distributed as if the inputs are Poisson, these actually are Poisson. Whereas when feedback is present, the only statement that can be made is that these distributions are the same as those which would arise if the inputs were in fact Poisson. Okay, so now everything is truly astounding, because by means of this incredible theorem, falsely applied to this complicated network, we get the right answer. And so what this means now is that this is just heaven for mathematicians, because the fact that you get the same answer means that if you make more complicated versions of this, you're still going to be able to solve the problem. So therefore, this is an applied problem. From the viewpoint of the mathematicians, this is the most amazing thing, because what you do is you introduce feedback, and you get the solution that would be true if a certain theorem is true, but it's not. Now you can imagine all kinds of variations on this, and you could see, in fact, that there are, from an application viewpoint, this is critical, because I could take a network that is in equilibrium and then introduce feedback, and the result will be to take the network out of equilibrium, because if I make, with this new lambda star, if I make the lambda star big enough, then what might happen is that some of the queues might become saturated, so that I could have infinite delays at individual queues and have finite delays at other queues, and that could all be the effect of the feedback. In fact, you can imagine the feedback probability as being a parameter that ranges from 0 to 1. You could adjust this. You see that when the feedback probability is 0, then the multiplying factor here is simply 1. If little p is 0, then what happens is that's 1, and lambda is the same as it was before. And if the feedback probability is 1, let's see, what will happen then? Well, if it's 1, things still might work out depending on the value of P12, because if everybody here feeds back, they still can go through and come out. However, if the P12 is big enough, then it's not going to happen and things are going to back up. Yeah? Okay, the lambda star. Now, this is not precise reasoning. This is the kind of reasoning that J.R. Jackson went through, and which is a sort of common sense reasoning. It's the only thing that makes sense if Burke's theorem holds. And you say, okay, what we're going to do is we're going to imagine that we break this loop. So we break the feedback loop. This is what electrical engineers do when they analyze feedback control systems. They break the feedback loop and they go from a closed loop system to an open loop system. And the open loop system has its parameters adjusted to take into account the feedback. Okay, so when I break the loop and have a new lambda, I'm going to call it lambda star. And what's it going to be? Well, imagine this is just some flow of stuff that comes in here. So there's going to be the same flow that you had originally, but then there's going to be the feedback, the flow that comes back. So how much is that going to be? Well, you take the amount that comes out here, and you multiply that by P12. That gives you the amount that goes to here. And you multiply that by P2. That's the amount that goes back. And you add that on to what you had before. So that's this term right here. But now, look at this. How much of this is going to come back? Well, the same fraction of it. So I take the same thing, and I multiply this amount by that thing squared. That is, imagine that it goes through here, and that accounts for this. And then I take this amount here, and I say, what fraction of that is going to now go this way, and come back? Well, the fraction of that that's going to do that is P12 times P2. So that means if I took this and multiplied it by P12 times P2, I get that squared times the lambda. But now, of this amount here, how much of this is going to come back again? Well, P12 times P of that, so that makes that. And how much of that is going to come back again? Well, P12 times P of that, which is going to give me to the 4th power, and so on. Yes. Yeah, that's stupid. That's P2, 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 P2. That's this guy right here, the probability of feedback. Okay, so this shows you the possibilities here. On the one hand, you've got practical methods to solve complicated systems. The thing to do is always to assume a product solution and then assume the simplest thing that the product solution could possibly be, and then show that in fact it works. That's the proof that it works. And then the reason it works is, well, I don't know the reason it works. It just works. It doesn't work because Burke's theorem applies, because Burke's theorem doesn't apply. But now from a mathematical point of view, you can imagine all kinds of proofs of how you can generalize things. For example, here we have only one class of traffic. Suppose that there were two classes of traffic to come out here, and maybe some of them had exponential service times with rate mu1 or mu2, and others mu3, and so forth. Suppose they were mixed, and suppose that some of them fed back, and one class fed to here, and you could imagine all kinds of changes. In fact, you don't necessarily have to have exponential service times. You could have something that's sort of related to exponential service times. We'll get into that later. So you could see that from the viewpoint of the mathematician, this is just wonderful, because that's what mathematicians want, is they want lots of problems that only they can solve, that are very interesting, and generally speaking, nobody else cares. But in applied mathematics, or where there are potential applications, somebody else does care, and so you get your salary paid. And you find yourself in a computer science and engineering department instead of a mathematics department, because they don't pay you anything in the mathematics department, because then you're doing things. In fact, in the mathematics department, if you start to do things that look like they might potentially have applications, then people don't like you, because then you're an engineer. So anyhow, that's exercise number 8. Now, another important one is exercise number 9. And with number 9, it's even more amazing, but it's sloppier. With exercise number 9, you assume that you don't have external output. External input. You assume something like this, although it's simpler than this. But suppose I had that. Suppose I started out with a fixed number of customers that were distributed throughout here, and then they just circulate. That model sometimes describes a computer science system where you have a bunch of jobs that are waiting externally, and you let some in, and they circulate, and then when somebody leaves, immediately you replace them with somebody else, so that the total number of jobs remains constant. And you want to know how long it takes the job to go through this. And surprisingly, then, of course, you're not going to have Poisson anything, because there's constraints that are going to make these things strongly dependent upon each other. But nevertheless, it turns out that you still get a product solution. And that's outlined in the book in exercise number 9. Okay, so you can see there's a lot of stuff going on here. Yes?
Exercise number 8 here. We assume that the service times are exponential.
Yes, we have to assume that.
Okay, and would the results still hold if they were not exponential?
No.
They would.
Well, for the regular Erlang-Loss model, if they're not exponential, it doesn't hold. Now, as you know from your homework, as the load gets lower, the dependency on the service time distribution gets less. So it might be reasonable to assume that if you don't have heavily loaded networks, that the Erlang delay models, that this idea describes it.
For low values of bandwidth.
For what?
Low values of bandwidth.
Yeah, you would expect so.
And what you mentioned about the feedback in the condition where the probabilities of feedback are very high, this would lead to some very large queues.
It could.
And what would happen to the results we obtain? What would happen to the whole throughput of the system?
Well, I think that as long as you have a row less than 1 at each queue, you're okay. But, of course, if the queues tend to get large, if you tend to have a bottleneck, and this is one of the practical problems, is finding these bottlenecks. If you tend to have a bottleneck, then the departure of the actual performance from what these formulas would predict would be greater, because as the utilization goes up, the assumption of exponential service times becomes more important in becomes more important in terms of agreeing with the formulas that assume that everything's exponential. But there are cases in which the service times are not exponential, some cases in which you can still get answers. And in fact, there's a whole area now, it's almost distinct from queuing theory, which is now called queuing networks. And there are books written on this subject alone. And when you start to look at these, you'll see that they're incredibly detailed. That things get very difficult very fast. But it's still true that people can get results out. And if you look in some computer science journals, like say the Journal of the ACM, there are often papers in there that have to do with queuing networks. because that's the main computer science application, and they almost all have to do with when there's a product solution of some type, or what you do when there isn't. I mean, that's basically it. If you take your standard courses in computer networks, ordinarily what happens is people assume that everything breaks down into node by node, and they assume that there's exponential service times every place, and then they use the formulas for MM1 usually, because these are usually one server channels. The question is, how accurate is that? Well, I don't know, but those things are based on the fact that based on these kinds of arguments. Now, so far, an interesting point is what we now know. Let's go back to the one where we had the external arrivals. Okay. For this case, we know what these probabilities are, and so we know that the number in each stage is independent of each other stage, and we know that we can calculate the behavior in each individual stage. Now, even though if I take a snapshot in time, the number in each stage is independent of each other stage, that doesn't mean that what's seen by a customer as he moves from stage to stage are independent. Because when a customer arrives, if he arrives at a snapshot time, an arbitrary time, then he sees the states with this probability. But when he leaves this state, he's now not seeing this state. What he's seeing now is the state of the system just having left there. And so now there's going to be a dependence between the length of time he spent here and what he sees when he leaves to get to here. So even though the number in system in each node of the network is independent of the number in every other node at a specific instant, it's not independent from the viewpoint of a customer who sees this and then this and then this and so on. So if I want to calculate the distribution of the length of time he waits, let's say the length of time it takes to go through here, I can't simply assume that I have these probabilities and calculate the waiting times here and the waiting times here and the waiting times here and then convolute them. I can't add them up as if they're independent of each other, but they're not. So it's very difficult to get waiting time or response time information in terms of distribution. But it's easy to get waiting time or response time information in terms of averages because of Little's theorem. Because Little's theorem says L equals lambda W. So if I look at this system, suppose I say, how long does it take for somebody from when he enters until he leaves? And now you look at this system and you say, well, customers enter at rate lambda from outside, and if everybody who arrives, that is, if none of these queues become infinite, that if we have stability everywhere, then everybody who enters eventually leaves. So there's a certain average number here, and there's an average time in this box. The average time, that's what we're interested in. That's the length of time it takes a customer on average from arrival to departure. Now, what's the average L? Well, that's the average number present in the box. Now, the number present in the box is the number here plus the number here plus the number here plus the number here at one point in time. And the average of that sum is the sum of the averages, so all I have to know at one point in time is the average in each piece. But each of those I already know because when we decompose the network, each of those is just an ordinary Erlang delay model with the appropriate value for the input. So I can calculate those things, add them up to get the average L, and then by L equals lambda W, I can divide the average L by the lambda, and that gives me the average time spent in the system. So it's very powerful in terms of what you can get, but there's still a lot that you can't get. So that's good, because that means that there's work to be done, dissertations to be written, money to be made. Okay, any other questions about this? All right, let me skip a couple of sections and go on to where do I want to go to? We go to page 171, called the method of phases. Then maybe I'll come back to some of this other stuff I skipped later, but method of phases is a good one now. So, before I start on the method of phases, where we are at this moment is if you're taking a course in computer networks, standard stuff, then all of the theory that they use, even though they don't really justify it in a course like that because it's the mathematics, which is sort of not the main point of the course. But all the theory that they used is really based on this stuff right here. This justifies it, or it doesn't justify it, as the case may be.
One thing about that, though, in typical computer networks, queues are not infinite, are they?
Well, nowhere can queues be infinite.
Well, I mean, they're not even large. I mean, they're not even.
No, they could be. I mean, first of all, whether it becomes large or not, in the design stage, you want to know whether it's going to become large or not. You don't want to have large queues. How do you know that? I want to be able to look at this before I actually build it and know that if I'm going to have a feedback beyond a certain critical amount, then this is going to have an infinite queue. So therefore, I can't have that much feedback. So I either have to increase the number of servers here or decrease the amount of feedback or something. So the theory helps you spot where the design flaws would be. That's one thing. And the second thing is that in things like internet, there may very well be gigantic queues because you got these data packets that are floating all over the place, and you know that if you send a message, email for example, it may appear in 3,000 miles away in an instant, but it may take an hour to get back to your own machine if you copy yourself, or it may take a day to get from here to Deerfield Beach. You don't know. And part of those delays must be queuing delays. And you know, for example, with America Online, that what they did apparently is they had a certain amount of capacity, and then they offered some freebies. They offered a service and they didn't charge anymore, so of course everybody took advantage of it, and the result was that the traffic increased much more than they expected, but the resources didn't, and then you couldn't get through because everything was backed up. It cost them a fortune. People complaining, suing, all kinds of things. And all they did basically was they didn't recognize that if they made an offer that would increase the load, that the increased load is going to have an effect on the performance. They didn't know what that was going to be, or they severely underestimated it, one or the other, and that got them into lots of trouble. Also, remember that we're talking here, the context you're thinking of is computer networks, but manufacturing systems are very similar. And in fact, in manufacturing systems, they have stuff like this now where they do things like they'll have a bunch of stations, and then what they'll do is, like with the design of wafers for semiconductor electronics, what they'll do is they'll send the stuff through a machine, and then they'll send it back through the same machine, and it'll go back and forth through here, and then it'll go to here, and back and forth through there, and then back there, and so on like that. And things get very complicated, and they got billions of dollars worth of equipment here, and what they want to do is they want to find out how to design this in such a way that they maximize the throughput. And so people are working on this kind of stuff. And in fact, if you attend some of the sessions in meetings from the people in Informs, mostly in the applied probability area, you'll see that the queuing network stuff is now starting to go into here. This is the next stage of amazing results. And people are finding interesting things like the shortest path turns out not to be the shortest path, that kind of thing. There are always strange bottleneck effects that can occur when you have feedback. Let me give you another example, which is not exactly related to this, but somewhat similar. This is the stuff that I've been working on myself, and we'll go into this later on in the course if we have time. Here's a network which models a local area network. So you imagine that you have a bunch of stations. This is called a polling model. and you have a single server, and the server serves stations. So the customers arrive to the stations like this, assuming, in order to be able to make this solvable, that we have independent Poisson processes, but different lambdas. So you might have lambda sub I is the rate at which customers arrive to station I. And typically, you don't have to assume that you have exponential service times, because as long as you have only one server, we'll get into this later on in the course. But the one case we have one server, which is called MG1, you can handle service times that are not necessarily exponential. So what we have is each one of these queues is an MG1 queue in isolation if the other queues weren't there. But they interact, because what the server does is it serves all of these messages, and then it moves from there to here. There. As a local area network, sometimes what you say is that there's a token, and that you release the token, which is just a signal, and the signal travels to here. And when it gets to here, if this station has any messages to transmit, then it seizes the token. That is, it gains access to the channel, and then it holds the channel until all of its messages are transmitted, including any that might arrive while the station has the channel. And then when it's done, it drops the channel, it drops the token, and the token travels to here and so on. And what you want to find out is, what are the waiting times, for example, in a single queue, as a function not only of the parameters for that queue, but as a function of the parameters for all of the other queues, because this is shared, this single server is shared among all the queues. It moves between the queues. So this is a very complicated problem, and it has a very unusual aspect, which is that when the server travels from here to here, work is piling up, but the server isn't doing any. And there are two kinds of time that can elapse when the server makes its travel. One is called the switchover time. So we have switchover time, which is, in the telecommunications model, that's the time it takes for the server to switch from there to there. And if this is a token, then this is the transmission time of the token, which may be significant compared to the length of time it takes to serve a packet. Okay, there's a switchover time. Then there's something called the setup time. The setup time comes from the manufacturing context, which is that when the server gets here, or equivalently, the server has different kinds of work it has to do. So what it does is it serves all the work of one type, and then when it's done with that, it switches to another type of work. And in doing so, it requires a setup time to change over from having its machinery adjusted to handle one kind of process to another kind of process. So in some cases, you can say that the switchover time and the setup time are the same thing. They're just different names depending on whether you're taking the viewpoint of a telecommunications model or a manufacturing systems model. But not always. And in fact, an interesting case is where you imagine that both occur. That first of all, there's a certain time it takes, you imagine, for the server to move from here to here, and then when it gets here, it has to set up. Now, if it always sets up, then these two things can be added together, and they can simply be considered to be the switchover time. But here's the interesting thing. Suppose that when you get to here, you notice that there's no work waiting to be done. Then obviously you shouldn't set up, you should travel on to the next queue. It turns out that that's not true. It turns out that sometimes when you get to a queue, it's better to set up even if nobody is there than it is to travel on to the next queue. Because if you solve the problem, you'll find that by forcing the server to set up even if nobody is there, somehow or other, the average waiting times for the whole system decline. It's also true, if that's true, it's also true that if you just look at the switchover time, for example, suppose you had a case where there were switchover times but no setup times. So all that happens is you finish here, you go to here. You finish here, you go to here. Now, it turns out to be true that sometimes it's better to slow the server down so that, in effect, you introduce dead time. That is, you switch from here to here, but when you get here, you don't start to work immediately. You wait a while, and then you start to work. And then when you're done there, you switch to there, but you don't start to work. You wait a while. It turns out that if you do that in such a way that you make the times you spend in traveling less variable than they were before, you smooth things out, that the end result is that the waiting times decrease. So we can actually show and give formulas that show how much idle time you should force the server to have in each cycle to minimize the total length, the total waiting time for the individual queues. So that's all very amazing and counterintuitive, and this is my particular area of research right now. So if we have time, we'll get into this. At least I can go into it a little bit more detail to explain qualitatively what's happening. I may not be able to describe it quantitatively, because the first thing you have to know to do that is we have to understand the MG1Q, which is the stuff that Chapter 5 is about. Remember, in this chapter, or in this course, up to this point, the service times are all either exponential, or it doesn't matter whether they're exponential or not. But if it does matter, then we don't know how to solve the problem. So this is stuff from Chapter 5. The general area is called polling models. And again, there are whole books written on polling models. This stuff began around the late 60s or early 1970s. And because of it's similar to this subject here, queuing networks. In fact, it's a different kind of queuing network. And it's similar in that there are applications in telecommunications, there are applications in manufacturing, and it's mathematically very interesting. So it meets the same requirements as this, although queuing networks are more developed than polling models. Nevertheless, there must be hundreds of papers in this area. So we'll get into that later. Okay, so back to the method of phases. The method of phases is the following idea. Suppose that I had a service time, or a length of time, that's exponential. And when it expires, I add on another exponential phase. And then I ask for the density function of the sum of the two phases. Or, suppose I had 3 phases. Time expires, I add another phase. Time expires, add another phase, and so on. In fact, what I could do is I could have a family of processes, family of distributions, in which the number of phases increases, and I could have the average length of each phase decrease in such a way that the average length of these processes is the same, but all that happens is they're composed of more and more phases. So if I plotted the density function, let me call f sub n of x. This is the density function for the case in which the number of phases is n. So if the number of phases was 1, then the density function would look like this. It would just be an exponential. If the number of phases is 2, then the density function looks something like this. If the number of phases is 3, something like that, and so on. In fact, the larger the number of phases, the more this starts to look like a normal distribution, which is what happens from the central limit theorem, because I'm adding up a larger and larger number of independent random variables. So if I let the number of phases get bigger, but make the length of each phase get smaller such that the average remains the same, I get a family of curves with a fixed average. Now, those are in the book. In fact, that's on the cover of the book. But it's in the book in Chapter 1. No, Chapter 2. Let's see if I can find out what page it's on. It's on page 66. There's a graph of it. Now, you can see, more or less, it's intuitive, that if I had any arbitrary density function, that I could approximate it by a density function that corresponds to a sum of phases. In fact, I don't have to have the phases having equal parameters. So I could imagine that I have a sum of phases, and the rate for this one is mu1, and the rate for this one is mu2, and the rate for this one is mu3, and so forth. So I could pick any number of phases I want, so I can pick any n, and I can pick any values of the mu's for the individual ones I want, such that their sum remains constant, and I can, in essence, fit any density function I want to something of this form. Now, you can prove that that's true. That's difficult proof, of course, to show that a density function of any form can be approximated uniformly, arbitrarily closely by a density function that has a certain specific form. But, well, it's just a mathematical theorem. And in any event, it's not really necessary for the argument that follows. Because what I'm going to do is I'm going to use this argument to show that in some cases it doesn't make any difference what they are, and that's going to be the basis for the proof of insensitivity. So the idea here is now that I'm going to imagine, for the sake of argument, that I have a loss system. So I have Poisson arrivals at rate lambda. But now, when I enter service, instead of having a service time that's an exponential, I'm going to consider the service time to be a sum of two exponentials. So let's say the first one has rate mu1, and the second one has rate mu2. So that means the average length of phase 1 is 1 over mu1, and the average length of phase 2 is 1 over mu2. And so I'll call that 1 over mu. So what I want to do is I want to imagine that when a customer seizes a server here, he stays in service for a length of time that's exponentially distributed with rate mu1, then for another length of time that's exponentially distributed with rate mu2, and then he leaves. And if he finds all servers busy, then he overflows. So this is an example of an Erlang loss system, because I have Poisson arrivals, I have block customers cleared, but I do not have exponential service times. I have service times that have a density function that looks like this, which is very non-exponential looking. So what I want to do is I want to solve the problem for this density function. And of course, as you'll see later, it doesn't make any difference how many of these mu's I have, and it doesn't make any difference what their values are, because the answer is only going to turn out to be in terms of this, which means that no matter how many phases and no matter what the parameters are, the only thing that counts is the average of the whole mess. Okay, once I do that, and you believe it, then you can see that, well, obviously, it doesn't matter what the service times are, and I get the same answer no matter what. So that's going to be my proof of insensitivity. Okay, so let me start by writing the equations for that. I'll just set them up, and then we'll worry about it next time. Okay, so we're going to look at a system like this. We have S servers. We have Poisson input at rate lambda. We have block customers cleared, but the service time is the sum of two pieces, one of which is exponential with rate mu1, and the other of which is exponential with rate mu2. And so now I'm going to let P J1, J2 be the probability that when a customer arrives, because remember we have Poisson input, so we have pasta, so it's the same as the outside observer, that the number of customers he sees in phase 1 of service is J1, and the number of customers he sees in phase 2 is J2. And then the objective here will be to calculate Pj. So once I have these probabilities, Pj will be the sum of those for all J1 plus J2 that adds up to J. In other words, the probability that the arriving customer finds J is the probability that he finds J1 in phase 1 and J2 in phase 2 added up over all customers in each phase, so that the total number of customers present is J. So I want to calculate these probabilities. So what I'm going to do is I'm going to write equations for these guys, solve them, put them in this sum them, and get this, and show that when I get all done, I'm going to have the Erlang loss distribution. And it doesn't make any difference what the values of mu1 and mu2 are, or how many phases I have. All that matters is that 1 over mu1 plus 1 over mu2 equals something, which I'll call tau. That's the average service time. Now, the point is, the reason I can do this is that as long as the phases are exponentially distributed, then I have a multidimensional birth and death process. Because if I know how many customers are in each phase, the length of time that the customers have been in that phase is irrelevant because they're exponentially distributed because of the Markov property. So what I'll do next time is I'll write the rate out equals rate in equations for this. No different from what I did before. Solve them, get the solution, sum it, and show you that the answer turns out to be independent of the number of phases and independent of the parameters of the individual phases. And so it doesn't matter. All that matters is the average of the whole service time, and it doesn't matter what the shape of the density function is. And that will then prove the insensitivity for the Erlang loss system. Okay, so we'll start there next time.